So let's switch gears a bit and let's talk about experiments. Specifically experiments to make your code a bit more sustainable, green, because that's nice, isn't it? We all want that. However, let's discuss a little bit why we would want that, because who cares about the greenness of a code? Code is just bits floating around in some cyber ether and doesn't really harm anyone, right? But the thing is that IT consumes a lot of energy. And with a lot, I mean somewhere around twice as much as aviation. Estimates vary. So as all kinds of industries are facing growing demands for greenness from regulatory and customers, so will IT at some point probably feel some of this pressure. Even regulatory, but certainly also from our customers, or customers, or what it might be. This means that being able to make our code green or more sustainable would give us a competitive advantage. It'll make us money. Yay! Now, how would we know if our code is green? We would have to measure it somehow. How do we measure the energy cost, or carbon cost of code? Well, one way we could go is to sort of measure the electricity used by the computers running it. You can use one of these thingies. Wouldn't give you good results, would give you results. About 100 kronas. But that's sort of difficult to use, really, because for once, your code might be running cloud. So how do you get the cloud vendors to put that in? Or some other data center who might not want things in their sockets. You might also trying to measure things on a laptop. Using this kind of thing on a laptop is just meaningless, because all you'll measure is how much you're charging the battery at any old time, and has nothing to do necessarily with how much energy the computer is using at the same time. But we can use indirect measurements, proxies. Cost is a great proxy. If it costs money, probably it takes energy. And if it takes energy, it most definitely does cost money. Another way is to sort of infer it from your infrastructure. You can look at your infrastructure code and see that this is going to cost that much carbon in a while. And there are ways you can do that. What we're going to look at today is very simple experiments with time, where we can use time, because that's highly correlated. Runtime is highly correlated with energy use in software. But there are also much more advanced ways we could go about this. Now, why would we want to experiment at all? We all know our code. It's good. But experience shows that our intuitions sometimes fail here. It's hard to know which is the most efficient, either in time or in space or in energy solution to any given problem. Also, we can get to show our work, put this in sustainability reports, and look really good, while increasing our confidence, well, at least decreasing uncertainty about our questions. And it's fun, I promise. Now, to the experiment. Say we want to know if it's faster to initialize a variable 10 million times inside of a loop, or do it once outside of a loop. We could just create some code that does those two things, measure the time, and output results. Unsurprisingly, in Python, you are able to see that you get some more. It's slightly faster to do this outside of loop once instead of 10 million times. Who knew? But what am I doing? This is NDC. We're supposed to do .NET, right? So in C# you can do the same experiment, and here you will see, of course, that it is very slightly faster to initialize the variable 10 million times inside the loop than doing it once outside. Java has the same result. I really don't know why, but it is consistent. Even adding consts doesn't help. Well, if you add const to one of these ways, the time used will drop to 5 milliseconds on my computer, but if you do it on the other one, you will have the same pattern again. If somebody knows why, please tell me. But to generalize the method we've been using here for this experiment, toy experiment, we see that we have a question. How much time does it take to initialize this variable? We design an experiment. In that case, it was code. In other cases, we might use this thing and see how much our screen uses various types of whatever. We run the experiment, execute the code, look at the monitors, and publish the results, like I just did. Let's look at another experiment. Let's see if we can see how much long does it take to parse. Is this the right one? No, this is the wrong one. Let's see how much time it will take to parse a bunch of dates. Because date parsing is something we do a lot. We have files that log files and such that we parse. We would want to design the experiment. We say we create a program that parses dates in different ways, all the different ways we can think about. We run this multiple times and varying order of things and all of that, and then we publish the results. And the code will look something like this, where you just run each of these date parsing methods and measure the time. For those interested, these were the results when I did this on this MacBook computer thingy. The fastest way to parse dates is using datetime parse. Try parse is somehow a bit slower in all instances. Parse exact is slower than parsing, so it's faster for .NET to guess the format of a date and then parse it than it is to provide it with the format for some reason. But this seems to be dependent on the format. And datetime offset is slower to parse than datetime. So you might think that you have to be some sort of genius programmer to code all these experiment stuff. This is how I coded this one. It was very fast. And LLM tools are very good at giving you code that answers your questions. It's horrible at answering the questions. I also tried having it answer my question, and it got it all wrong. Speaking of questions, there are a few types of questions we can ask and that we can do experiments on. The types, at least the experiment designs have been answering thus far, is of the type is A better than B, better than C, better than E. And this makes for very simple experiments. So these are good questions to sort of hack out an experiment on. Easy to interpret results usually. Another type of question is, what is the best way to do X? Or worst way? This is very hard because now you need to know that you've been able to find all the ways or all the relevant ways to do X, which I didn't in my datetime parsing experiment, for instance. There's one I missed. And it can be, but these can be refined into more decidable questions, often of the type, is A better than B? And the last kind of question is, so what is the impact of X? These are very interesting questions often, but also fairly difficult. So let's look at one of those. So what is the impact of using Rust in Azure functions through WebAssembly? Because Rust can compile to WebAssembly. And WebAssembly is fun. So how do we figure this out? Well, we have to create several Azure functions that do different things, and we used code from a paper ranking software languages by energy use, because we figured out that we couldn't just take any old code. We needed to take some code that was sensible or had some meaning. And we figured that those guys got published, so they probably had some meaning behind the code examples. Running it several times in the cloud. And these were, of course, the results, as you can plainly see. Drilling a bit down, for those interested, Rust performed on par-ish with Node, I would say. C# was by far the fastest way to execute these functions from this ranking paper. And Java, for some reason, was really, really slow on Azure functions. I cannot fathom why Microsoft would do such a thing. This is a while ago. It might have been fixed. This is the ranking I was just talking about. And you can rely on these types of rankings, especially when they're peer-reviewed and all that, at least to a certain degree. And in this ranking, we see that we got this sort of pattern we would expect, compiled down to machine code languages are the fastest generally, with some exceptions. Virtual machine codes come in somewhere in the middle, like Java, C#, those kind of things. And interpreted languages like Ruby and Python end up at 70 to 80 times slower than C, 20 odd times slower than Java, C# and those kinds of languages. But let's look at one more experiment, because I wanted to test this out. Was it true? So what is the fastest programming language, C# or Perl, when running regular expressions and almost nothing else? Show of hands. Who think C# was fastest? 1, no, 2, 3, some? Perl? Oh, Perl fans in the audience. Great. I made this code. I got, again, ChatGPT to help me with the Perl thing, because I really don't understand that. But it worked, and it seemed to give some results. I even got it to tell me how many results it got from parsing email addresses out of a fairly long document. And results? Perl is 5-ish times faster than .NET for this exact workflow. And the point I'm trying to drive home here is that this is very dependent on context. You need to know what your code is, what it does, in order to know which choices to make. And that's really it. If you'd like to learn more about this, shameless self-plug, come to the workshop on Friday, 10:20 in workshop room 1, and you'll get to do these experiments yourself. Thank you.